Okay, let's talk about chi-square distribution today. And using chi-square distribution, we can check if the observed dataset is distributed as the expected distribution. So, chi-square distribution, since it's squared, it gives you a distribution that is only on the positive values, that is on the x-axis, you will get only positive values. And notice how chi-square distribution changes as degrees of freedom increases. That is, the sample size goes up. It becomes more symmetric. Now let's see how can we check that whether our observed dataset is distributed as expected using Excel. For this, we need to determine the null and alternative hypothesis. Just like before, we have the null hypothesis that the random variable follows a certain distribution, and there is an alternative hypothesis that null hypothesis is not true. And for this, we have certain conditions. These conditions need to be met. I just want to clarify one thing. Notice this expression. So expected counts are n times the probability, and pi by I usually we mean cases or rows in the dataset. For example, if we flip one coin, the chance of getting a head is 1/2. Now, if I say I flip 10 coins, then n equals 10 and p equals 1/2. So I can expect 10 times 1/2 equals 5 heads showing up. And that's how we measure the expected counts. Okay, now let's consider this problem. An obstetrician wants to know whether the proportion of children born on each day of the week is the same. She randomly selects 500 birth records and obtains the data shown in table 3, this table. Now, do we have a reason to believe that the day on which a child is born does not occur with equal frequency? Ideally, we would expect 1 out of 7 chance for each of the days out of 7 days a week. But as you can see, the observed dataset shows that more children are born on Wednesdays, Tuesdays, and Thursdays. So how can we check if the observed frequencies are different from expected frequencies? Our null hypothesis is that the proportion for each day of 7 days are equal, and that is theoretically equal to 1 over 7 because there are 7 days in a week. And the alternative hypothesis is at least one of the proportion is different from others. We set a level of significance alpha equals 0.05. Now, the expected count for each category day of week, assuming the null hypothesis is true, is 500 over 7. That's because we have 500 cases here. Now we have both observed and expected frequencies. Now let's use Excel to calculate the chi-square. So I have the dataset entered here, and the sum of all these numbers, that means the total number of children, is 500. The observed frequencies are listed. The expected frequency expected is 500 times 1/2 n times p. That means 500 over 7. So now we can calculate the difference between observed and expected values, square them, and divide by the expected value and put it here. Observed minus expected, and we need to square them and then divide by the expected value. Now we have 9.05257 as the result of this exercise. If we double click on this little rectangle, we get the values calculated for all these rows. Now when we sum all these numbers, we get the calculated chi-square, which is equal to what we have in the slide. You might wonder what is the sum of these values. This is 500 because in total we have 500 students equally distributed in their probability, in their frequencies. So now we have the calculated chi-square, and we want to check if it's beyond the critical chi-square. If it's beyond critical chi-square or bigger than critical chi-square, then we reject the null hypothesis that there is no difference between observed and expected value. But if it's smaller than critical chi-square, then we fail to reject the null. Essentially, what we are trying to do is to check if this value goes beyond this threshold level, and the threshold level is determine the level of significance that we chose. The shaded region is alpha, or the area that shows the critical region. 0.01 is our level of significance. And we have seen in the class how can we use this table to get the significance level and the associated probability and the chi-square scores, chi-square statistic, but we can also use Excel to obtain that. For example, if we already know that there is alpha equals 0.01, that means we want to be 99% confident. And degrees of freedom here is 7 minus 1, because we have 7 observations here, and we are losing 1 degrees of freedom because we are using the expected value. Now we have alpha and degrees of freedom. We want to know what is the critical value for this threshold. And let me write this down. This is chi-square calculated, but we want the critical chi-square. So for that, we choose chi-square dot. Notice we know the alpha, we know the degrees of freedom, so we want inv dot rt. Inv is invert. Inv is inverse because we know the probability, we know that alpha equals 0.01. What we want is the score, the value, the 16.812. So we want this alpha here, and we know the degrees of freedom. So degrees of freedom is 6. Press enter, you get the score here. Alternatively, we could have done we could have done a p-value method. That is, what is the lowest alpha where this value is on the x-axis. This value becomes the threshold. So we are talking about the region right to this value. So if we do that, we can use a different formula, and that is chi-square dot dist dot rt. Notice I'm using rt because we only need the values from the right tail. We are not doing like z or t-score. We are not doing a two-tailed distribution, two-tailed check. It's just one tail, whether this value is bigger than this threshold, and that's all. For that, we already have this value, the chi-square, so 19.568, and we also know the degrees of freedom, that is 6. Press enter, you get 0.003. That means the value, this region, this blue region here, beyond this point 19.56, that value is 0.0033. And this alpha or this p-value is less than the required alpha or zero point 0.01. So in both cases, we reject the null hypothesis. Why? Because first, the chi-square, calculated chi-square is bigger than the critical chi-square. So that's classical method. And second, the p-value beyond this chi-square, calculated chi-square, is smaller than the required alpha or level of significance. 0.0033 is smaller than 0.01. So we reject the null. So in conclusion, there is sufficient evidence that the day of the week on which a child is born occurs with equal frequency can be rejected. So that means the null hypothesis that we set, that all the probabilities are equal, we reject the probability because our observational data say something different.